Hey guys, I wanted to go over this problem that we really talked about a lot in class. Actually, I'll go over another one too. So we have this diagram with discrete energy levels of an atom, and an electron in the n equals 4 states, it tells us is going to jump into the n equals 2 state and emit a photon of a particular length. So let's just kind of draw that jump down, and then the photon is emitted of 121.9 nanometers. Okay, and it asks us to find the energy level of the n equals 4 state. So what we need to do is figure out, okay, well, if it started at some energy state, ending at this energy state, negative 13.6 electron volts, if I want to know where it started, I need to know how much energy it lost. So that means finding the energy of the photon, right? So find the energy. And remember, that's hc over lambda, and I'm going to use that number from class, that class for hc, that 1.24 times 10 to the third electron volt nanometers, and I calculate by plugging in that E is equal to 10.2 electron volts. So that means they gave off 10.2 electron volts to go from n equals 4 to n equals 2. That means it must have had 10.2 electron volts more at n equals 4 than n equals 2, which means that if we just add 10.2 to this number, we get negative 3.4 electron volts as the energy at n equals 4. We want to find the momentum. Remember that momentum, de Broglie wavelength equals h over the momentum. So momentum equals h over the de Broglie wavelength, and we know the wavelength is 121.9 nanometers. We plug it in there. H, we're going to now use the joule seconds version if we want momentum in kilogram meters per second. So H equals 6.63 times 10 to the negative 34 joule seconds, right? So we'll plug in that, we'll get our momentum, and that's 5.9 times 10 to the negative 27 kilogram meters per second. Hopefully you're getting that. If you're not, we got issues. We should talk about that. It's really not that hard. Okay, now C and D, totally different problem, except that the same photon hits a silver surface in a photoelectric effect experiment. Remember, photoelectric effect, energy goes in as light, goes out to do two things: to get the electron free and then to give it energy. Okay? It tells us the work function's 4.7 electron volts. So remember, we're putting 10.2 electron volts in, that's the photon. And that becomes the work function plus anything left over can become kinetic energy, right? The work function's given is 4.7 electron volts. So 10.2 EVs equals 4.7 EVs plus K. K equals, man, this is really hard, 5.5 electron volts. Okay? Stopping potential for the emitted electron. Remember, the stopping potential is what we got to crank the battery to stop the electrons from moving, to cancel out their kinetic energy, right? Now, we were talking about this at the end of class. The hard way to do this is to think, okay, K, is equal to the U of the electron, potential energy of the electron, which is Q times V. So we know K, and now we're going to solve for V. But if we want to do this, and we want to get a voltage in volts, and we're going to use a charge in coulombs, then kinetic energy has to be converted to joules. To convert the kinetic energy from electron volts to joules, we're going to have to multiply by 1.6 times 10 to the negative 19 coulombs. Joules per electron volt, I'm sorry. So we're going to multiply this by 1.6 times 10 to the negative 19 to get it into joules. But then the very next thing we're going to do is divide by Q, 1.6 times 10 to the negative 19 coulombs, to give us the voltage. What that really means, guys, is that the easy way to get the voltage when we have the kinetic energy in electron volts is, rather than multiplying by 1.6 times 10 to the negative 19 and then dividing by 1.6 times 10 to the negative 19, realize we don't have to do any of that and say the voltage, the stopping potential, is 5.5 volts. Okay? So remember, stopping potential in volts equals the kinetic energy in electron volts. It's just the same number. It's trying to be your friend. Let it be your friend. Okay, next video we'll talk about another problem. See you in a bit.